Hi, I'm Guang, 50 years old, secondary 3 from NES High School. In this lesson, we will be taking a look at the techniques of limits calculation, more specifically, using your gamma function. Alright, so we will be taking a look at two different examples, but they look quite similar in terms of what kind of methods they were using. And if you have seen our last lesson, the methods would also be similar to what we had before. Alright, so first of all, you would want to recap what is so special about your gamma function. So of course, let's say you have, starting from a gamma A, well this is just a recall. If you want like more detailed explanations, you can go back to previous lessons and all. Alright, so let's say you have gamma A, then you would be having integrate from 0 to infinity. Whatever you use here, you can use t, you can use x, whatever you like, alright? So e to the power negative t and t to the power of a minus 1 dt. Alright, so this is your basic definition for your gamma function. Now, some special things about your gamma function. Let's say you have just gamma a. You can change it into a minus 1, then gamma a minus 1. Alright, so these are some of the basic things that you would want to know when you solve these questions. More of the second one and not so much of the first one, alright? For the first is if you just started and you want to write every step very specifically about how you solve everything, alright? So now let's get into the questions. Alright, the first example, we have limit n approaches to infinity. 1 minus 1 over 3 square times 1 minus 1 over 5 square times 1 minus 1 over 7 square until 1 minus 1 over 2n plus 1 square. So how about let's change this into the pi notation first. Now how would this look like in the pi notation? Now in the pi notation, over here it would be 1 minus 1 over 2n plus 1 squared. So that means your n would start from 1 until infinity. Alright, so this is what you're going to see for the pi notation form of this limit. Alright, now how about we combine them a little. So when we combine them, you would be seeing 2n plus 1 squared in the denominator, while for your entire thing, you will have 2n plus 1 squared minus 1. Alright, so of course you will want to expand the term above. When you expand it, you are going to see 4n squared plus 4n plus 1. But that plus 1 will be cancelled out with the minus 1 behind. So it's just left with 4n squared plus 4n. Alright, so this is what you have. Now how about we divide it by 4 in both numerator and denominator? Well, at the same time for your numerator, since if you divide by 4, you'll be left with n squared plus n. So you can also take out an n at the same time. So above you have n times n plus 1. And this thing is divided by 4. So divided by 4, you're going to see n plus half squared. Alright, so this is what you are going to see. But beware, in the previous lesson, we used the Wallace product. And yes, we are going to still use the Wallace product. But this time, you have to be aware that this is n is equal to 1. That means you have to change it into n is equal to 0. But how do you change that into n equals 0? Well, of course, the first term will be shifted a little bit. That means your entire function, it will have to look a little bit different, but not too much different. So when this becomes a 0, so your first term, that means your n, it would need to be able to still have 1. So n plus 1 would just be n plus 2. But for this part below, since you add 1, so you have n plus 3 over 2 squared. Right? So now you can use your Wallace product. Now Wallace product, you have 1, 2, 3 over 2, 3 over 2. So 3 over 2 plus 3 over 2 is equal to 1 plus 2, which satisfies the condition in order to use your Wallace product. Now how does it go now? So what you would see is gamma 3 over 2 times gamma 3 over 2. Beware, it is kind of inverted. So gamma 3 over 2 squared over gamma 1, gamma 2. Alright? So gamma 1 is 1, gamma 2 is also 1. Well, in a previous few lessons, we also showed what gamma half is. And if you can recall earlier in the lesson, we also said a very important thing about gamma function, where you have, let's say, gamma n, that would be, you can make it n minus 1, gamma n minus 1. So in this case, we are going to use that. Now you will see, I'm just going to make this a square bracket, half gamma half squared. Alright, since you have two of them, you're going to use the same thing. Well, for a denominator, they're both ones, so it's not going to matter. Now, half, what is gamma half? Now, gamma half in the previous lessons, we have already shown that it is square root pi. So, square root pi squared, you're going to see pi over 4. Alright, so this is the answer for your first example. Alright, so now let's take a look at the second example, where we have limit n approaches to infinity, 1 minus 1 over 2 squared times 1 minus 1 over 6 squared until 1 minus 1 over 4n plus 2 squared. Alright, so this example, we use a similar method, but how similar exactly is this method? So firstly, we would also change into the pi notation. The pi notation, where here you would have 1 minus 1 over 4n plus 2 squared, while n actually starts from 0 this time. So it starts from 0 and ends at infinity. Now this seems simpler than a previous example, right? Since this directly starts from 0. We'll see later on. Now, how do we continue? Well, we would just, again, combine them into one fraction. So 4n plus 2 squared, and then 4n plus 2 squared minus 1. Okay? So that part in the numerator, we can expand it. Pi notation, and from 0 to infinity. And in the numerator, you're going to see 16n squared plus 16n plus 4 minus 1, which is 3. And then over 4n plus 2 squared. Alright, then how about let's divide by 16 on both numerator and denominator. So this is what we are going to see. Now of course, in the numerator, we can again factorize. So in this factorization, we are going to have n plus 3 over 4 and n plus 1 over 4. So in this case, we can once again use what we have done before, the Wallace well, whatever you call it, formula, whatever. Alright, so then it will be changed into gamma half, then over gamma 1 over 4, gamma 3 over 4. Wait, at this part, it seems like it's unsolvable since we do not know what gamma 1 over 4 is, right? Well, we have another formula for this part over here. Well, we would have, let's say, gamma A multiplied by gamma 1 minus A. Well, A is bigger than 0, smaller than 1. So, A, then you are going to have pi over sine A pi. Alright, so this is what you're going to have. Well, in this case, you can use either 1 over 4 as A or 3 over 4 as A. Both of them, you can use it since it is just sine. In the first quadrant and second quadrant, they're all positive. So, of course, you can also think about it the same for the part above since half and half, they add together to become 1. Or you can just plug in square root pi to form pi over. So down here, you have pi over sine pi over 4. Is that right? So that means this is just equal to sine pi over 4, which is square root 2 over 2. And that is the answer that you would get. So in these two examples, we have used two important formulas, or you could say they're both formulas, or one of them would be specifically called the Wallace product. So if you really want to see what the Wallace product exactly looks like, then it would be pi notation, and from 0 to infinity, then you have, let's say, n plus a, n plus b over n plus c times n plus d. And this is gamma c times gamma d over gamma a times gamma b. But there is a condition. Well, a plus b is equal to c plus d. Alright, so these are the two important things that we have used over here. But for these, why do they work? Well, you have to stay tuned for future lessons where we actually prove it. Alright, so that's the part for solving the questions. Do you find anything special about the questions that we have done, whether it's this lesson or in a previous lesson? Well, if you have found something special, then what is it? Now, if you haven't found anything, let me give you a little clue. What kind of number are all of these? They're fractions, right? Okay, so they're fractions, that means they're rational numbers. Rational numbers can always be expressed as fractions, but what do you realize about the final answer? One of them, you have pi over 4, the other, you have square root 2 over 2, which makes them irrational numbers. So, isn't that kind of weird, where you have a lot of rational numbers, you multiply them together, and you get an irrational number. So, you see, when a rational number multiplied by a rational number, generally you would think that what you get is still a rational number. But apparently, when you have infinite number of rational numbers multiplied together, then you won't be really so sure about it. You would have to actually go and calculate it to see whether it is an actual irrational number or it is maybe just another rational number, maybe more complicated and all. Okay, but that is one interesting and weird thing about these examples involving stuff like Wallace product, your gamma function. In the end, a large portion of it, or even just a portion of it, will actually end up with irrational numbers, even though you started with all rational numbers. Alright, so I hope for this lesson you're clear of these two examples so far. Well, you have to be aware again of your formula when you come to unsolvable cases, but you do have a special pattern with it, or your Wallace product. And also beware of conditions and where it starts. Alright, so I'll just end this lesson here, and thank you for your watching.